This question here. The hoop rolls down a hill of incline 30 degrees without slipping. Find its linear acceleration. The moment of inertia of a hoop about an axis through its centre perpendicular to the plane is given by I equals mr squared. Okie dokes. So, just 1 second. I'm just using I can't find my book, I need to find my book. So here we go. Okay, number 7. Hoop rolls down a hill. Now, lads, unlike the last one, okay, this is a hoop, okay, so basically it's like a hula hoop, okay, it's not full in the middle, so it's just basically a ring, okay. So the ring on the outside is, so you imagine the black line is the only piece that actually has mass here, okay. Now, because of we're going to do what we did last time, 30 degrees here. Even though it's a hollow hoop, this, by symmetry, the centre of gravity still has to be in the middle. Okay? Then we can do gravity going directly down. Gravity going directly down. Then resolve the two components parallel and perpendicular. Okay, so what we're going to get here, what is the weight of the hoop? Doesn't say, so we're just going to assume it's m. Okay? So the weight of the hoop is going to be mg. It's going to be 30 degrees. Lads, 30 degrees. Cos 30 degrees is what? Can anyone tell me? Cos 30 through 3 over 2. Sin 30, a half. Okay. This makes this root 3 over 2 mg going this way, and then a half mg going to the right, okay, and down. Now that's done. What we can do next is the gain in kinetic energy equals the loss in potential energy. So the gain in kinetic energy equals loss in potential energy. Okay, so gain in KE equals loss in PE. So it's what we did last time. So half mv squared, because you're gaining linear, plus a half I omega squared equals loss in potential energy, which is going to be mgh. Now, h, as discussed before, if that's my drop in height, and this is my distance s, and that's 30 degrees, then basically sine 30 equals h over s, therefore h equals s sine 30, and we know that sine 30 is a half, so it's just going to be a half s. Okay, so we're going to get a half mv squared plus a half. Now, what does it tell us about the moment of inertia of the hoop? So we just had to replace that with mr squared. Omega is what it was last time, phi squared over r squared. mgh is going to be mgs over 2. Multiply them out. A half phi squared plus a half phi squared equals mgs over 2. The m cancels. Okay. Phi squared therefore equals gs over 2. Now we want to find out the linear. We want to find out the acceleration, linear acceleration. Okay. Now linear acceleration is going to be a equals, phi squared equals u squared plus 2as, and then phi squared equals gs over 2, u squared is 0, 2AS is going to be 2A times S. S cancels on both sides. 2A equals G over 2. A equals G over 4 ms to the minus 2. That's handy enough, right? Now, the hardest one on this full thing is the next question, number 8. It's a step up from what we have been doing. Okay? Huh? G over 4. Okay, the next one, which is an annulus of mass m has an outer radius r and an inner radius r. Prove that the moment of inertia of the annulus about an axis through the centre is perpendicular to the plane is a half m r squared plus r squared. Have we done this before? Can anybody remember? Have we done this before? Lads, we've done this already. It was on exercise 14A, question 3. You can check back the video to find that one there. So, also what we need to take home from this is that our annulus is, its moment of inertia is r squared plus small r squared, okay? So, what we're next doing is we're going to do the, what we're next trying to figure out is basically, we're on part 2 now, okay? So that's all part 1. There's 2 different ways of doing part 1. We have the conventional way, that's in the solutions. Now we're on part 2. Yes?
Question 6, not question 3.
Okay, it was question 6. 14A, question 6, not question 3. Okay, part 2. Gain in kinetic energy equals loss in potential energy. Okay, let's figure this out. So, what's happening is a light inextensible string is wound around the outer rim of the annulus. The free end is fixed to a point on the ceiling. So we're going to draw our diagram. Oh wait, other side. Okay, very similar to the question we just had earlier, wasn't it? Except this time, it's not a full disc, it's basically a ring, okay? So, that's the difference between this one and the last one, okay? Now, it's wound around the circumference, is that what it says? It's falls freely under gravity around the outer rim of the annulus, okay? So, I was to draw this string in green. Okay, so what we're doing next is green gets wrapped around, okay, and then it's going to fall under gravity. Now, we have the forces are tension, we have tension going up. Once again, by symmetry, the centre of gravity has to be located in the centre of the disc, okay? So, mg going down. And now we're going to do our gain in KE equals loss in ME, the usual, okay? So, gain in KE is a half mv squared plus a half I angular speed squared equals mgh. Next step, a half mv squared plus a half. Now, we have to replace in I with what we got a second ago. That part there, a half m, big R plus small r squared. Big R is from here to the outer rim, small r to the inside. Okay? And then that's all going to be then w squared, which is going to be, now is w going to be phi squared over small r or phi squared over big R? How do we know? It's big R, but how do we know it's big R? Because the string is wrapped around big R, not small r. Yes.
The first big R is squared as well.
Okay guys, it's a half mv squared is the kinetic energy. This is the rotational kinetic energy. I is the inertia of the hoop, and we know that from part 1. the proof that was on exercise 1. Replace I with a half m r squared plus small r squared. Now I had to figure out what is the story with the angular velocity. Now the angular velocity is how fast it's rotating, but because the string is wrapped around the outside, big R, not small r, that's why the angular velocity is usually, trying to think of the formula now. Oh yeah, phi equals r omega. It's big R because it's the big radius, and that means omega equals phi over r. Omega squared equals phi squared over r squared. Okay? Now, what we're going to do next is half mv squared plus a quarter m. Oh, also equals mgh over the other side. Okay? Equal to mgh. Now, what we're going to have here is quarter m. We're going to have r squared plus r squared. Put the phi squared in there. All over r squared equals mgh. Get rid of the m's. Now, we could do it getting rid of that fraction, okay? So let's multiply both sides by 4r squared. 4r squared gets rid of everything. So we're going to have 2 phi squared r squared. Then we're going to get rid of that quarter by multiplying by 4. And what we're going to have is, we're just going to have phi squared into r squared plus small r squared, because the big r squared cancels with the denominator here. Okay, multiply the other side by 4r squared, and we're going to get 4ghr squared. Okay, factorize and keep an eye on what we're looking to prove. We're looking to prove acceleration. If we get velocity first, we can get acceleration second. We're always using phi squared equals u squared plus 2as. If we get phi squared on its own, that will lead the path to getting a on its own. So what we do is factorize out phi squared, and we're going to get 2 big R squared plus R squared plus small r squared equals 4ghr squared. 2 of these combined gives you 3r squared, so phi squared therefore is equal to 4ghr squared divided by 3 big R squared plus small r squared. Use the formula phi squared equals u squared plus 2as. Phi squared equals 0 plus 2as. Replace in what phi squared is. Phi squared is 4ghr squared 3r squared plus r squared. Divide by 2, and s is missing, isn't it? Oh yeah, s is h. Get rid of the h's, and I'm going to get a equals 4g r squared divided by 2 multiplied by 3 r squared plus r squared, and what happens to the 4 and the 2? 2gr squared over 3r squared plus r squared. Is that what they asked for? Take out the mg. Oh, that was for the tension now. Okay, yeah, proved. Now part 3, still not done yet, unbelievably. 2 big R squared, 3 big R squared plus small r squared. Okay, in this question, the linear acceleration if we go all the way back to the start, it's going downwards. Net force equals weight minus tension. So, part 3. Net force equals weight minus tension. Net force going down, weight going down, tension going up. Net force is mass multiplied by acceleration. And acceleration, as we know, is this here. Weight is mg, tension is minus t.
It's 2g or so. Yeah, but I think it's g. Yeah,
I'm missing a G, am I? Yeah. Yeah. Lads, above the dotted line, okay, I had my G, so I forgot about my G in the answer, okay? So there's my G there. So what I'm going to get is tension to the left, all of this to the right, so I'm going to get tension equals mg minus mg multiplied by 2r squared divided by 3r big R squared small r squared. I'm going to get next is factorise out the mg and get 1 minus 2r squared bracket 3r squared plus r squared. Mg into 3r squared plus small r squared minus 2 big R squared all over 3r squared plus r small r squared. Mg into r squared plus small r squared 3r squared plus small r squared. That was asked to prove. Okay.